ready to start. So I'm very happy to be introducing Alessandro Chiesa, who's a professor at EPFL. Today he's going to be giving a talk about something which we hope is close enough to something that interests you guys, which is about the recent line of work about getting very efficient proximity test from like linear code with minimal properties. Take it away.
Thank you, Giacomo. All right, cool. So it'll be a somewhat technical talk, so please, since it's a longer one, do interrupt me along the way, and I'll try to answer questions as we go, okay? So this talk is about IOPs. We've already seen them in the morning, so I'm just going to flash the diagram, all right? So an IOP is an interactive protocol where the prover has oracle access to, so the verifier has oracle access to the prover's messages, okay? Why do we care about IOPs? They're essentially equivalent to hash-based succinct arguments. If you give me an IOP and even fairly weak hash functions, such as a collision-resistant one, I can construct for you an interactive succinct argument. And conversely, if you give me a succinct argument based on ideal hashing, then I can pull out from that an IOP. Okay, somehow it's a very kind of fundamental object of study, right? And we care about hash-based succinct arguments very much for a number of reasons. They are post-quantum, and we've seen from today's talk from Justin that it's something that we should have and want to deploy. Okay. Today specifically, we'll also talk about the relaxation, interactive oracle reductions. It's just like an IOP, but instead of the verifier making up its mind, it produces another instance. And so this is basically a fancy word for a reduction aided by oracles from one relation to another. And from the perspective of this talk is just building blocks towards IOPs, okay? We'll kind of make our way slowly from some complicated relation to a simpler one, in particular a trivial one, by way of IORs, okay? Interactive oracle reductions. Again, so I think you've seen in Pratyusha's talk, some of you earlier today, a number of IORs, and you've seen how, at least on the quest of query optimal IOPs, how interactive oracle reductions play an important building block role. Okay, so that's as much I want to say about these. I don't want to like belabor them because maybe many of you have sat through a number of talks about them. Are there any questions at this point before we move on? Should be fairly clear. Okay. All right. So the message I would like to kind of come across today is like, where do modern IOPs come from? Right? We have like a stork here bringing a baby IOP. And kind of the established answer that we inherit from a line of work on probabilistically checkable proofs is that you arithmetize some well-chosen NP problem, maybe like circuit satisfiability or 3-sat. And then, having arithmetized it, you locally test a resulting kind of a property about a polynomial code. Okay? And to some extent, that's been the case well into the arc of research of IOPs, but I would say that at least at some high level, things look a little bit different today from this established answer. And maybe the way we look at IOPs today is a little bit more refined, where you kind of you pick a linear code, something quite unstructured. In fact, it could be even maybe a random linear code. And you pick some structuring operation. So this structuring operation could be something like interleaving or tensoring, and you just give a tiny bit of structure, and you obtain some kind of barely structured code. And you're gonna construct an IOR from your well-chosen NP instance to some encoded problem with linear constraints over this minimal structure, such as an interleaved code or a tensor code. And after that, you construct an IOP of proximity for this problem, okay? And what's the point of this refined answer is that, at least personally for me, this looks more like an arithmetization and then a polynomial code, but more something that is like truly like kind of linear code native. Like there's barely any polynomials. We'll be seeing some multilinear extensions, but to me, it's like a bit of a far cry from the kind of algebra-intensive constructions that kind of we inherit from the efficient PCP literature, and then we feel the inertia of that in the first few years of IOP research, right? So I think we've kind of come in a different place right now. So today, I would like to have tried to distill from the last few years some maybe pedagogically simple construction of an interesting IOP purely from interleaving. And okay, I'll try to highlight that construction. I think it's just useful to keep in mind, and you can somehow branch out from there into, like, I think, maybe state-of-the-art constructions, using that one as a kind of a compass to kind of keep you grounded. Okay, so that's the plan. So any questions so far? Good. At some point, someone is going to have to ask a first question, right? So it's a safe space here. All right, so we're going to be working with linear codes. So let's just put it, I mean, many of you know what linear codes are. I just do this primarily just to get a common notation between us. Code is a subset of points in some kind of a subset of vectors in some space. What is interesting about codes is that they have small, like the distance between any pair of elements in the code is bounded away from zero, like some sort of constant relative distance. You can imagine these balls around all these points that don't touch each other. And we'll care also about encodings. So there are two views of codes. You can either think about them as subsets or as like a procedure that takes a message and then maps into this subset. So we will care about encodings as well. So it's just some way to take a message space into that code. We'll care about linear codes. That just means that the space in which we're mapping into, it's an F-linear space. Think about it as some kind of vector space F to the D for some dimension D, finite dimension D. In this case, the minimum distance is just the minimum number of non-zero elements of any code word. And you've seen from Dan's talk the notion of list decoding is a fundamental property of codes. So for a given distance around a vector in this space, you can count how many code words are within this radius. That's called the list, right, of this code up to a certain distance. If you go up to the distance of the code over 2, you can find at most one code word. And if you go beyond that, you'll find a few more. And one of the things that we've learned in designing efficient IOPs is that we have to make sure to work at distances where this list is not too large. Otherwise, we don't know how to design kind of protocols that are sound. Okay, so that's all the notation we're going to need about linear codes. It should be, I think, a good review, particularly for those of you who sat in Dan's talk. For relations, we're going to use standard notations. I'm going to go through I'm not going to go through it carefully, but we have relations. You can project to just the instances of the language, and sometimes I may care about fixing an instance and looking at all the witnesses for that instance. Okay? All right. Good. So now we get to, I guess, the start of the actual talk. All right? So my aspiration is to go through this blueprint. We're going to have two parts to this talk. In the first part, I'm going to explain what used to be in the old, let's say, blueprint for algebraic constructions, the arithmetization. But today, I think it looks more like just a combinatorial encoding of the witness. Okay? I'm going to show how, using an IOR, we can start from some well-chosen NP-complete relation. You can think about these as non-linear relations, because there's always some kind of either quadratic equation somewhere, right? And you start with an instance and a witness for this NP-complete relation, and we're going to create distance with relying on any code. In fact, it doesn't even have to be linear, right? It just has to have good distance. Okay? This is going to make our witness, in some sense, even a little bit larger, right, to create this distance. But then, now we have some relation that is kind of simpler, okay? By way of this IOR, we'll end up with subproblems that are linear. They're not quadratic, okay? And so we'll have some encoded relation that involves linear constraints. And once we are there, we'll see that it's kind of quite easy to select a sequence of codes that gets smaller and smaller and have IORs that shrink our problem through operations that we'll see. And along the way, we'll barely need any structure of these codes. We'll just need interleaving. That's it. And to a first order, a lot of the kind of modern IOP constructions follow this paradigm. Of course, if you want to strive for optimality, for example, today, we know how to get query optimal IOPs, not from interleaved codes alone, but we need tensor codes. But again, I don't want to talk about like optimal IOPs. I just want to get to like a respectable IOP that reflects the the way of thinking of modern constructions, and that a lot of interleaving, and kind of that's it. And that's kind of the beautiful thing, that it's a lot less algebra than we used to have. So I will probably spend maybe around 10 minutes, hopefully, on this part 1, and then spend the rest of the talk on part 2. It's an aspiration. Somehow I don't believe I'll be able to go through all of it, but I will try to go slowly, and at least for the parts that we do see, hopefully you will kind of learn something, okay? Are there any questions now? Still no. Please, there should be a question at some point. Okay, so that's the blueprint. Good, all right. So we're gonna start with part 1. We'll see a kind of transformation from an NP-complete problem to an encoded problem, okay, with linear constraints, okay? And kind of the main idea of this we often call this a preamble of the protocol, right? It's just kind of getting to the point where you can start really doing probabilistic checking. We want to create distance. Okay, so I want to define more precisely what are these kind of encoded relations that we're going to use. So this is not the relation we're going to use, but it's kind of a warm-up to it. So the kind of relations that allow for proximity testing are things of this sort. You have some message here called a Z. You encode it into a code word F, right? And you consider the relation consisting of valid code words of the code. Okay? Now, by itself, it's not a very interesting relation because it doesn't tell us anything about satisfiability of anything, right? So we need to kind of embellish this relation a little bit. So we can sort of encode and program into it some interesting kind of properties. So this takes us to another, I think, very elegant kind of basic relation is like the previous one, but we just add some linear constraints on the message. So again, we're going to ask that there is a valid message underneath the code word, but this message is not just anything. It's something that satisfies a list of linear constraints. How many? Well, for now, think about it as a constant, maybe 3 or 4. Eventually, we'll accumulate constraints that grow proportionally with the security parameter. But you should think about the number of constraints as not being too large, right? Something that you're willing to pay for in query complexity. Okay? There is no quadratic equations here. Intuitively, it is because we're going to shed them in that first preamble, right? We can get rid of quadratic equations and only survive with linear constraints thereafter. Interesting to see that such relations, deciding them is kind of in P, right? Like, but nevertheless, we'll be able to reduce to such relations from NP using interaction. Okay, so this is our target. We want to sort of take our satisfiability problem and map to such things, and then for such things, we will construct IOPs of proximity. Okay. So in the instance here, X is gonna kind of keep track for us the specification of these constraints. So we have a vector Vi, that's kind of a coefficient vector, and tau I is the kind of target value, right? And kind of the question we're asking, is there an underlying message that satisfies, I don't know, 5 linear constraints for 5 specified vectors and targets inside the instance? Okay. I'm shoving under the carpet a couple of things, for the experts among you. Like really, at this point, typically we work with ternary relations where we have an explicit instance, an implicit instance, and then a witness. I'm kind of hiding the implicit instance into the witness, whatever. Like so, if you look in the literature, you will find some kind of small mismatches. It's just for pedagogical reasons. Any questions? Yes. That's right. So I was exactly referring to the fact that typically it would be part of the witness, and you would consider what is here the witness as implicit input. Okay. Yeah. So for now, I just kind of consider. Basically, there is a dual view of proximity tests. Is the oracle given directly to the verifier an implicit instance or a witness? Like both are valid syntactically. It's just more convenient to make it implicit instance in formal treatments. For the talk, I'll be taking the view of the witness is eventually given as an oracle to the verifier. Okay, good. All right, so that's the target. The starting point is going to be some well-chosen NP relation. Unsurprisingly, it's going to be, for the purpose of this talk, R1CS. which I remind you are kind of well-structured quadratic system of equations. You know, matrix A times vector xw, matrix B times vector xw. Take entry-wise product, and you get that kind of a matrix vector product. A, B, C, and little x are part of the instance, and big W are the witness. Okay, and you know that's kind of the picture you should have in mind. You have these matrix vector products, and the entry-wise product just means that I'm comparing, you know, the entry-wise product of the A and B kind of inner products, matrix vector products to the C one. Okay, good. This should be like quite standard. All right. So the only polynomials we're going to use in the entire talk are multilinear extensions. So there is this EQ polynomial, which is a low-degree extension of the identity on the 0, 1 kind of Boolean hypercube. Okay, so you should imagine you have n variables x and variable z, and this EQ polynomial has specifically value 1 on the diagonal, where x and the x's and the z's have the same bit string value, and off diagonal it's 0 because they're not equal, and outside the kind of 0, 1n cross 0, 1n is just whatever. Okay? And this one lets us talk about multilinear extensions. We'll talk about multilinear extensions of matrices. So a matrix, even a rectangular matrix with m rows and n columns, you can literally extend it with the corresponding EQ polynomials. Okay? All stand. Yeah? There is a y that could be a z, could be a y. At least it's self-consistent there, but yes. Yes, maybe I should have used y up there. No, this one here, yes. This one should be a zi, sorry. Yes, I was looking down there. Good, all right, I can fix something already. And it's a multilinear extension because you can imagine in this sort of a rectangular world, u is placed onto this kind of 0, 1m cross 0, 1n, and then outside is whatever, right? Okay. Good, all right, so the point is that you can map R1CS into a collection 4 linear constraints quite easily, and then what you end up is with an encoded relation. We're just going to see it quickly, see the protocol, and move on. So you have these matrix vector products, and in particular, I can look at them as a multilinear extension matrix times vector, and this gives me a natural kind of linear constraint with an indeterminate, right? So I'm interested in matrix A, B, or C times vector Z. I can replace sort of the matrix with an indeterminate here, right? And I get that this polynomial, if I were to evaluate it on 0, 1 to the m, I would get exactly the inner product that I'm looking for, which is that matrix times Z, right? Why am I writing it as a polynomial this way? Because at some point, I'm going to be using sum check. Okay, good. So it's just kind of a clear, yeah, I think I have it over here, that yes. This polynomial can be viewed as taking the matrix vector product and then extending, right? Okay. So why are we doing this? Because you can take the satisfiability condition of R1CS and write it as a vanishing condition of multilinear polynomials. Okay, you give me A, B, C, and Z. This relation happens if and only if this polynomial vanishes everywhere on 0, 1 to the n. Okay, these are all pretty standard kind of things that you should have seen before. We have a vanishing condition. That means that we can bundle it up using another EQ polynomial into a summation condition, which is a sum check condition. Okay. Any questions about this one? I think this is all, I think, basically any standard sort of kind of snark that uses some IOP behind it, even polynomial IOP, and if it's about R1CS, it's likely going to use some variation of this kind of setup. What's the takeaway? What we're about to do is that this setup is compatible with like basically any code. I don't need like any structure from the code to talk about it. So here's the protocol. So we see the protocol and we can move on. The prover will assemble the full vector from the instance in the witness. And then given any code, really any code, it will just encode that full satisfying assignment and send it over as a code word. That's an oracle. Okay? Actually, I think this is going to be the only oracle in this protocol. The verifier sends over some randomness for the reduction from vanishing to sum check. And we run the sum check protocol as a reduction on this claim. Okay? Why this claim? Because look, we were interested in this part vanishing on 0,1 to the m. And so this one reduces that vanishing claim to a summation claim. And that's what we wanted to do. This sum check reduction yields a claim that says the add-ind evaluated at a random point where you replace B with the randomness that the verifier injected into the sum check protocol will yield some claim of this form, right? This one, the verifier can evaluate by itself, and this one, it will need help from the prover, okay? So the prover will say, okay, yeah, you cannot evaluate these things by yourself. Here are the values, alpha, beta, and gamma for these three guys. The verifier will just check that claim, assuming those claims are correct. And now the verifier can just prepare what are the leftover, now linear claims to pass on, right? So using the identities before, the coefficient vector that is relevant here are these three, which are known to the verifier at this point. It has the matrices A, B, and C, and can just write down these coefficient vectors. Then there is like a little technicality around the input consistency. I'm just going to gloss over that. Doesn't matter. It is in the slide for completeness. The point is that now we have reduced satisfiability of our 1CS to a claim about an encoded message in an arbitrary code. I don't even need linearity. And these three linear constraints on the message, and some other linear constraint for input consistency. So a total of 4 linear constraints. And so in here, when I look at a protocol like this one, I'm like, look, there's like barely any arithmetization here, and surely we're not relying on any property of the code, not even that it's linear, okay? In fact, the fact that it works for any code, you might ask, but does it even have to be a code? Where does it matter, right? So I'm going to get to that in a moment and see exactly the point where the code comes up. Because when you need the code to have property A, B, C, and D, it's kind of, okay, whatever. Like, it needs 10 properties, so I can only use these codes. When you can use any code, then it will be like a very well-identified place where the code contributes and only contributes, right? Okay, any questions about this protocol? We're almost done with part 1. Good. Yeah, sure. Yes, so at least for this kind of a protocol, let me get there. The verifier has A, B, and C, and it can compute these, because of course it also has rows, so there's nothing that depends on the witness here. This can be done in like linear time. If you want to run in time that is sublinear in A, B, and C, which we do in practice, you would have to move these to a holographic kind of pre-processing stage, which is that you can also do, but it's a more complex protocol. But yeah. So maybe let me add that I will not be like focusing on like a sublinear verification, but just on a kind of a bare bones kind of a good query complexity. Okay, good question. All right. So where does the property of the code come up? So it's pretty easy to prove that if the instance is not satisfiable, then no matter what the prover does, the probability that the output instance is not in the output encoded relation is bounded by order of m plus n over f. You can just see where the soundness errors come from. You have some soundness errors in bound link, the soundness error of the sum check, and the soundness error of the input consistency. Those are the only the only randomness of the reduction, and they each contribute some errors. This is not enough for local testing of the output claim, but what you can prove, and this is, I think, pretty amazing, that it really at a small price in error, you can prove a strictly stronger claim that if the original instance is not satisfiable, then you pick any distance you want, target distance, of course, again, against any prover, the probability that the output is delta far from any valid message that satisfies those constraints is at most that same probability blown up by the list size at delta. And here is like really a minimal, like very clear place where the code comes up. And the reason why you want the code is because in such reductions, what controls soundness is the list size at the distance you're targeting. And so what the distance contributes is that because we will eventually want the distance to be, let's say, constant or even very close to 1, having a good code is what keeps this list under control. Okay, and nowhere else. Like in this reduction, you don't need it for anything else. Okay, so I think that's what I wanted to convey, that you can take NP and convert it into like an instance of this encoded relation with linear constraints. And there is really no structure needed from the code other than being a code and having bounded list size. Of course, you can set the distance to be within unique decoding. This distance will be 1. You can also set it beyond it. It will be whatever it is. Right? You just need to be able to afford it relative to m plus n over f. Okay, so we're about to transition to the other kind of part. Like, any questions here? To me, this is like a canonical modern reduction from NP to encoded instances. Like, it kind of summarizes kind of the common core of kind of many of the IOPs that we have out there. Yeah, good question. Yeah, I don't see where it would come up also. Yeah, I think this works really for any code. But I have to yeah, I don't think so. Yeah, good question. More questions? Okay, good. So there's like interesting kind of optimization. Sometimes if you don't like list size times sometimes that one, you can add out-of-domain samples to kind of pull it out and kill it via separate out-of-domain samples. All right, so takeaways, we had NP, a well-chosen instance, and as ingredients, an arbitrary code, multilinear extensions, some check protocol, and now we have reduced the problem to local testing of sync-coded messages with linear constraints. There is all kinds of embellishments you can add, zero knowledge, holography we discussed. You can start from other nice NP relations, and as long as they're like reasonable, you can sort of adapt this approach to some of these. Okay, good. So we've seen this part, okay, which is about creating distance. We haven't used much from the code other than the distance. And now we've landed over here where we have some linear relation with, in this case, we are starting with 4 linear constraints. And now we're not done yet, right? Like we have a problem to solve. And the approach in many constructions is to go through a sequence of iterations to make the problem smaller and smaller, okay? The nice thing is that each of those iterations are kind of small and cute, and you can sort of really understand them in detail, and you just then concatenate it, okay? So now, with the remaining 25 minutes, I just awarded myself 2 minutes, we'll see some of that. Okay, and this is where we'll start using some minimal structure, specifically interleaving. Okay, so I'm going to go through a quick warm-up. I think Pratyush already went through it this morning, so I think I'll do it pretty fast. So remember, interleaving is an operation where you kind of stack code words and then you rethink the alphabet size vertically in these columns, right? So the picture is this one. You have an interleaved code word. So you have this factor of interleaving. You take the code and you kind of consider k code words stacked over each other, but now your alphabet symbol is like a column, right? Interleaving preserves linearity. And if you have an encoding for the base code, it gives rise to a natural encoding for interleaved code where you just go by rows. Some people like to think of interleaving in the transpose way. I'm sorry. I think interleaving is totally stacking this way. I don't like hanging the code words next to each other because, like, imagine they're dangling somewhere. Like this way, they're like, they're like on top of each other, right? But it's just big endian, little endian thing, right? So, all right. So, if you don't have constraints, if you just look at the encoded relation with no constraints, going from an interleaved code to the base code is kind of pretty straightforward. So let's say that you wanted to design an IOR from a relation with no constraints over the interleaved code to the base code, which is like a smaller relation by a factor of k. You just do a random linear combination. And Dan gave a fantastic talk that talks about how you can relate distance about these original kind of interleaved code to the distance of these kind of derived linear combination, right? It's kind of not hard to see that if you're not trying to create distance, not being in the code will lead not being in the code with high probability, but it gets much more as a deeper question if you want to preserve distance. If you start out delta far from the interleaved code, you want to be bound the event that you drop below delta. Sorry, this would be greater or equal to delta, right? So start at least delta, then at least delta except for some probability. Okay, another typo there. Okay, and this leads to the question of distance preservation. I don't really want to go over it. Dan went over it at length. Basically, it says you can define the property that you need to get that IOR to work. For that specific IOR, it's enough to have like a weak notion distance preservation, but in many other settings, you want this more. You want more mutual critical agreement. Won't go through it. It's not the focus of this talk. The point is that we have such notions, we have such results, and the takeaway is that if you don't have linear constraints, kind of reducing the problem size is just a problem of distance preservation, and that's it. It's essentially equivalent to it, okay? And what I want to try to explain and convey is how can we reduce also linear constraints, which we have, right? Like we started from an NP, we ended up to an encoded relation with linear constraints. So we have to be able to kind of shrink linear constraints as well as we go forward, right? If we go from an interleaved code to its base code, we also need to carry forward these linear constraints. And also, once you reach the base code, what do you do? And so this will lead to like a beautiful notion of code switching that kind of permeates a lot of the constructions of IOPs, right? And I think I have slides that sort of get to the point of each of these kind of core ideas in some sort of isolated, kind of pedagogically simple setting, okay? So, so we'll see now how to fold code and constraints and then hop to another code, okay? So that's basically the strategy of modern IOPs. Are there any questions about this? Yes?
So for the first part of the talk, you said that we didn't need to assume anything about the code.
Yeah.
For this part, you're assuming linearity.
Yeah, so for this part, we'll use two kind of orthogonal properties. So interleaving, we'll use it as a tool. Interleaving, by the way, makes sense also for nonlinear codes, right? And then linearity. Linearity is simply because once you interleave and you want to shrink, like you kind of need to have something to rely upon to shrink, even without constraints. If you just give me an interleaved code word and I want to kind of reduce to the base code, I'm already using linearity just for this, even before I hit constraints, right? What is, I think, surprising is that that's it. Like, nothing else will matter to get to the end of this, okay? Now, there are other things you might worry about, like the efficiency of the verifier. Is it linear or sublinear? Then maybe you need slightly more structured codes. But if you don't care, you just want good proof length and good query complexity, interleaving and linearity will be enough. Which, again, I think it's interesting to stand back and appreciate. To me, this is not the way we think of PCB constructions, for example, right? Or early IOP constructions. All right, so now we're back to local testing with constraints. All right, so I'm going to outline the strategy, let's call it fold and hop. So here's a strategy we're going to take to reduce the problem size. So we're going to start out with some interleaved code with linear constraints and rely on a IOR whose entire job is to reduce to the base code, okay, with the linear constraints. Now we're kind of stuck, right? In principle, we don't know where else to go. And the idea is to hop back to an interleaved code. So here we're shrinking the problem. Here we preserve the size of the problem. We're moving back to a structure that allows us shrinking further. Okay? And this basic gadget just is repeated over and over, okay? Until you feel like it's enough and you just trivially solve the problem. You just ask the prover, send me the witness, I'll directly check it, right? So as you go through, your problem size may start, I don't know, at n, and then it goes to n over k1 because we're shrinking by a factor of k1, right? Across the hop, it doesn't get smaller, but then we shrink again, right? And that's how it works. We kind of accumulate these shrinking factors. Now you might ask, wait a second, like, why are we doing any hops? I could just pick my shrinking factor to be huge to begin with. There's a trade-off. And the trade-off is that your alphabet size in this IORs is going to depend linearly with K1. So like you have to read K1 alphabet symbols over here. You have to read K2 alphabet symbols over here. So you cannot afford blowing up these shrinking factors. Common settings are either constant, logarithmic, or square root, okay, depending upon kind of your target. Further, because we'll be working with sum check, we'll assume that all the relevant quantities are powers of 2, but again, symptotically it doesn't really matter. But that's the strategy, and in a sense, the moment I give you these two mostly unrelated IORs, you can really like construct this in some configurable way, and that's it. That's how you construct an IOP of proximity for linear constraints. Okay? Questions? So the plan now is that we'll talk first about this one, and then if there's time, that one. But I think I will be able at least to talk about this one. Yeah? Now, some of the optimizations I'll briefly mention have to do with how to magically choose these factors as you go through, choosing the codes to make certain things happen with distances, right? And then other things that are have nothing to do with this specific structure has to do with bringing in tensor codes for special tasks. But that's for optimizations. I think this is kind of like the I think the pedagogical core. I think. All right. So at high level, what we're going to do is do something like a random linear combination, but not quite. It will be like think about it as a systematic random linear combination. And that's something that we can call an interleaved fold. Okay, I'm going to define an operation for you. So I have some function defined that over some number of field element of alphabet symbols. These are large alphabet symbols. Okay, so now I have little k. You should think about it as 2 to this little k is big K, but now it's a power of 2, so I'm making it explicit that it is a power of 2. So I have sigma to the 2 to the k, and I want to kind of shrink the alphabet size by folding around some field element. Okay, and this is the mapping. Okay, I don't want to go through it. I have like a picture for that. So this mapping, what it does is you take every location of the function, which can be seen as a vector because this is a large alphabet symbol, right? You take this large alphabet symbol, you disassemble it into 2 to the however many coordinates you're folding around. Okay, so this one is I field elements, so you disassemble it into 2 to the I pieces. Each of the I pieces will have size 2 to the k minus 1. And each of those pieces, you take this sum. Okay? What is that sum? We'll interpret it later. For now, it's just some other linear combination. Instead of being like kind of fully random, it's just some other coefficient vector that is related to EQ. The role of EQ here is that somehow it's doing a sum in the systematic part of the code. Okay, and we'll see later how this one kind of matters. Okay, so that's like interleaved fold. So far, it just seems like some whatever operation. I will, I think, in the next slide, tell you like what is its properties. Okay. All right. So there's some nice properties. The first one is that it commutes with code encoding. I can fold an interleaved code, or fold first and then interleave less. And either way, I'll get the same thing, right? So that's nice. Another property is that it interacts nicely with constraints. Okay, I can take some constraint, right? I can define, so you give me a target vector and a message z. I can define this multi-quadratic polynomial q sub coefficient vector and message. I can define this multi-quadratic here. And it has the property that the linear constraint of v and z can be expressed using this sum check-like claim. Okay? Why? You know, because, but the because fits here. Okay, I don't really want to go through it, but it's just true. Okay? And somehow the fold operation is chosen to make these things happen. Okay, that's what's special about it. All right? So we didn't have to consider something like this when we didn't have constraints because we didn't care about these other things, so it was enough to consider a random linear combination. Here we'll consider some other random-ish linear combination defined by EQ so that these things happen. Why do we care these things happen is because the next slide we'll see an IOR for shrinking or mapping from interleaved code with constraints to the base code with constraints. Okay, so these things are chosen to make that happen. Yes?
Do you need now that the code is systematic?
No, I guess I'm using systematic in an intuitive sense, but yeah, I think maybe systematic is not the right word. It's more that I've defined like a message space somewhere and I'm reasoning directly about the message space. But yeah, the code doesn't need to be systematic. Good question. All right, so just see the reduction. So what I want is I want to kind of do what I was doing before. Before we saw how random linear combination goes from interleaved code with no constraints to base code with no constraints. Now I want to do interleaved code with, let's say, one constraint for simplicity to base code with also one constraint. Okay, so I'm shrinking the code and the constraint at the same time. So look, we just argued that there's a certain sum check claim that is the constraint, so we're just going to run that reduction. Okay? So we run sum check on this one. Okay? That will spit out a claim that will say this multi-quadratic at a random point equals some value that comes out of the sum check protocol, whatever that is. And okay. If we go back to, so this one I can define as the new virtual oracle. Why does it make sense to consider this one? Because remember that folding commutes with encoding. So if I'm folding the encoding, it's tantamount to folding the underlying message, right? So therefore, it makes sense for me to define the coefficient vector on the target this way. Because remember, this guy was tracking the inner product of the folded message and the folded coefficients. So the folded message is secretly inside here. I mean, not secretly, but it is inside here, the encoding. I folded the code word that is tantamount to folding the message. The coefficient vector, I fold it, right? And the target is whatever the target is comes out of here, right? So that's it. That's my new constraint. And one can prove that if your original claim is delta far from a message that satisfies the constraint, then with high probability, so is the output claim. The high probability here curiously depends both on list bounds and on MCA errors. Okay, that it shares very much the protocol, the properties that you saw, for example, in Dan's talk when he talked about this like elementary toy protocol that had a contribution from the MCA error and the list size, and the same thing is happening here. Notice that syntactically we are running a sum check protocol here, but from an analysis perspective, something much more interesting is happening because we don't just get the soundness error of the sum check protocol. That's not what's happening, right? You are getting some sort of kind of MC errors corresponding to the intermediate interleavings on the way to the base code. Okay? So in my mind, I view this one as kind of the kind of canonical basic reduction of an encoded problem with an interleaved code to its base code with linear constraints. Okay? All right. Any questions? All right. So I have 6 minutes. I'm gonna skip over handling multiple constraints. The FYI is that it's not a problem. You just batch them. I want to just conclude with the hop. Okay? Actually quite simple. So let's say I have two codes. Let's say they're mostly unrelated. All I care about is that they have the same message space. Okay? Because look, they have to encode the same thing, so they should at least have the same message space. And the goal is we want to, without shrinking, go from an encoded message with linear constraints to, again, encoded message under the other code with linear constraints. We may have a few more linear constraints, that's fine, right? We will need that C1 is linear. Anyways, C2 is going to be linear for other reasons later, but at least for this protocol, we need C1 to be linear. By virtue of being linear, we can write down a generator matrix for its encoding, right? And I'm going to need some notation to talk about its rows. So each symbol of the encoding of a message is a specific inner product between a row of the matrix and the message, right? That's what it means to be like a kind of a linear code. But also remember that because we may have large alphabet symbols, each alphabet symbol may contain, I don't know, D1 field elements. So I have a block of D1 rows that together construct the D1 field elements of that symbol. So I'm going to use this I, j pair to consider the ith symbol, jth location of that symbol. Okay, good. That's all the notation that I need. And the takeaway is that we can express every field element in an encoded message as a linear constraint. That's good, because this leads to a very nice, cute, simple protocol to go from code 1 to code 2. So here it is. So we're starting out with an instance under C1. So we have some message encoded under C1 with some number of linear constraints on it. What the prover is going to do is just send me an encoding under the second code of that message. Okay, so that's an oracle. What the verifier is going to do is to spot check linear constraints from F1. Concretely, we're going to have some security parameter t, think about it as lambda, sample some number of locations, read those locations from F1. Those result into linear claims, right? Like each of these symbols is intended to be a collection of D1 field elements that are supposed to be the inner product of this row of the matrix with the message. So I just write that row of the matrix into the vector. And I just carry those along. I have the original linear constraints and I have the new linear constraints corresponding to the spot checks. And one can prove that this works. It's distance preserving, okay? So for any delta, if F1 is delta far from anything under C1 that satisfies linear constraints, with high probability, this other thing is delta far from C2 to satisfy those other linear constraints, okay? And like before, if you don't like the product of list size and whatever is the soundness error, you can always break that relationship with some out-of-band sampling. Okay, it's just the same thing as before. Okay, that's it. So this is code switching. There's other sorts of code switching out there, right, that use, if you know a little bit more about C1, a little more about C2, then there might be other protocols you will be able to run. In this case, it's like a generic code switching. Okay? Good. All right, so I want to wrap up. I have 2 slides on verifier efficiency that I will not give. They have to do with basically what you do if you want succinct verification. So I'll skip over those and conclude. So if you are wondering about constructions that you have in your mind, how do they sit? In some sense, what we talked about is something that works with any linear code, with interleaving, supports linear constraints, and then we have, like, I've shown you how to handle list decoding. But it's mostly like extrapolating from a body of work that is showing a number of beautiful techniques for how to handle either constraints or no constraints, shrinking, but all of this with interleaving, right? So interleaving appears in important ways in many of these works. You've seen other talks where, there's also interleaving can be used also as a subroutine of a bigger strategy. Tensoring can also come in. But as far as today is concerned, this talk was just about how far can we go with interleaving and linearity alone. And the takeaway is that even with the modest structure of interleaved codes, you can get remarkably efficient and useful IOPPs. Okay, that's really, and I think it's an interesting takeaway. This looks not the way I was thinking about probabilistic proofs maybe 10, 15 years ago. But today, like the things I described are extremely efficient and kind of really practical. All right, so that's the blueprint that we saw. Encoding using a generic code, and then assuming linearity and using interleaving to fold and hop, fold and hop, fold and hop, until your problem size is of something that you're willing to solve trivially. I'll put a side plug, which I mentioned also in the other talk, just in case there's a set difference. We're starting to do like a significant post-quantum expansion of ArcWorks, and happy to kind of establish further collaborations around that. And I think with that, I'm gonna stop here, and I'm magically on time. Yeah.
Also the previous slide, I think apparently we kind of converge to the same protocol. So with Hirito, you can also with just like one more linear plane.
Whoops.
Have,
no, sorry, you mean this one?
Yeah, you also have like ballistic coding.
Okay, yeah, no, but I presume many of these, if you just sit down, you
converge to
yeah. More questions?
I think just one question, so give me time.
Wait, what, sorry?
One question.
One question for...
Let me ask,
So all the linear constraints you consider are always...
Maybe I just... Yeah, okay, pass it back.
So all the linear constraints you're considering are always over the finite field. But in some cases, like our data is inherently in a group, like an elliptic curve group, for example. So does all this generalize to linear constraints over groups rather than just finite fields?
A good question. I think, so linear codes, you can leave them to be over modules, right? And so it could make natively sense over groups as well. Mm-hmm. And I think what would be missing at that point is having, I guess, MCA statements at that level of generality. I think if you were to get them, then I don't see anything that would specifically break here.
It's interesting, by the way, SumCheck easily
easily
generalizes to that.
Yeah. I think it's just MCA, and it doesn't seem, look, for the best statements about MCA, I mean, I don't know whether they generalize, but at least the ones that we have about linear codes, they seem, maybe they would go up to modules.
I see.
Yeah.
Cool.
Yeah. Thanks for the question.